Alrighty everybody, welcome back to Acorn's Academy. In this video, I'm going to go through a summary, comparison, contrast, and decision making for the substitution and elimination reactions SN1, SN2, E1, and E2. If you've been following my videos thus far, we've covered all four of these reactions, including some important considerations for carbocation stabilities and rearrangement. So today we are going to put all this information together. We're going to figure out how we can tell which reaction is happening, and then we'll do an example problem. Let's get started. So you might recognize this table. We've been filling out this table in each of these four videos for each of these corresponding reactions. And now that we've filled the whole thing out, added some details, now we can really start to see how things are comparing. So the first thing I'm going to do, I'm going to compare SN1 and E1. We can see that they are both stepwise. They're both unimolecular. They both like bulky substrates. They both require a weak reagent, not the same reagent. SN1 is a nucleophile, E1 is a base, but both weak regardless. Both of these end up with a mixture of some sort, and both of these have polar protic solvents. So just looking at the SN1 and E1 characteristics and properties, we can already tell that these are extremely similar reactions. And two reactions that are very similar are often very fiercely competing. So anytime I am given a bulky, like a bulky substrate, like a tertiary alkyl halide, with a polar protic solvent, immediately I have to start balancing out between SN1 and E1. And I'll show you an example of how you can tell the difference. Now moving over to SN2 and E2, we can see that they're both concerted. They're both bimolecular. Substrate-wise, they're not exactly the same, but E2 can happen with a primary substrate. They both require a strong reagent, again a nucleophile for substitution, a base for elimination. Stereochemistry-wise, they're not the same necessarily, but they are both very specific, right? So this is 100% inversion, this is beta antiperiplanar. So there are very specific stereochemical requirements for SN2 and E2, as opposed to SN1 and E1, where it's just a mixture of everything, right? It's not really all that neat and clean, whereas SN2 and E2 are very neat and clean. And then SN2 is polar protic, and E2 can have all of them. So looking at these two, again, we can tell that SN1 and E1 are probably going to be our fiercest competitors because almost everything is the same about them. So I have this handy dandy flowchart that I like to use. It's a framework for determining what reaction is going to happen. There's the actual flowchart at the top, and then there's this portion at the bottom that I call additional considerations. These are extra things to watch out for, and I'll get to these in just a minute. But I'm going to start here. So the first thing that I'm going to do is I'm going to look at my substrate. That is the number one thing I want to look at. What kind of substrate am I working with? And I have three options: primary, secondary, tertiary. There are methyl and also allylic, benzylic, alkoxy, alkyl, so there's a variety. But it's going to be some sort of primary, secondary, or tertiary. So let's start with primary. If I have a primary alkyl halide, so something that looks like this, and I react it with a strong nucleophile, what kind of reaction do you expect? Right, SN2. I expect an SN2 reaction. Strong nucleophile, primary alkyl halide, and we can see that right here. Unhindered primary with a strong nucleophile, that is directly SN2. Okay, now if I take that same substrate, and I react it with a strong base, like ethoxide, hydroxide, or terbutoxide, what kind of reaction do you expect then? Yeah, E2. So in the case of a primary alkyl halide, we are going to get either SN2 or E2. These are our options. There is no SN1 or E1 with a primary alkyl halide. Okay, I'm actually going to go ahead and skip over to tertiary real quick. Let's go to tertiary. Oh boy. All right. So if I have a tertiary substrate with a weak nucleophile, what kind of reaction do you expect? Yeah, SN1. Remember, this is a nucleophile. So one of the substitutions, and it's tertiary, so it can't be SN2. There is no SN2. Make that look more like a 1. All right. Now, if I have that same tertiary alkyl halide, and I instead react it with a strong base, then what kind of reaction do you expect? Yeah, E2. So an E2 reaction. Remember, again, E2 is strong base. So if you have something that is a strong base, it will be E2. All right, and lastly, if I have a tertiary alkyl halide with a weak base, what kind of reaction do you expect then? Yeah, E1. So notice for tertiary, there is no SN2. SN2 does not occur with tertiary substrates. Okay, so now we get to arguably the most convoluted one, and that is secondary. Secondary alkyl halides are infamous in undergraduate organic chemistry courses because they can undergo all four. Right? At least for primary, it was only the bimolecular reactions, and for tertiary, we know SN2 isn't going to happen. But for a secondary alkyl halide, we can have any of the four. So I've again analyzed the substrate. Now I'm going to analyze my reagent, whether or not I have a nucleophile or a base. So if I start with my nucleophile, if I have a secondary halide with a strong nucleophile, what kind of reaction do you expect? Again, SN2. Okay, strong nucleophile, SN2. Now if I have that same halide with a weak nucleophile, what kind of reaction do you expect then? Yeah, SN1. You can start to see the strong-weak correlation here, right? Strong is bimolecular, weak is unimolecular. Okay, if I go all the way to the right here, if I have a secondary alkyl halide and a base, a strong bulky base, what kind of reaction do you expect then? Yep, again, E2. And lastly, a secondary alkyl halide with a weak base is E1. Now, I want to make an important note about these two. I'm going to highlight them. These two. The problem that we're going to encounter with SN1 and E1 is that most weak nucleophiles tend to be weak bases and vice versa. So the reality that we have to accept here is that any time for at least for a secondary alkyl halide, and most certainly probably for tertiary as well, anytime we're dealing with a weak nucleophile, we're also probably dealing with a weak base, and therefore we are likely to get both. So what I'm going to do is I'm going to write in small letters here, just like right next to it, I'm just going to write or E1 for this, and then I'm going to write or SN1 for this. Because they are very fiercely competitive, and we saw this here. Right? Remember we looked at SN1 and E1, and we said that literally everything is the same, like almost everything is identical. There was a reason for that. Right? They are very fiercely competitive. Okay, so now let's go ahead and look at some of these additional considerations. So if we have a protic solvent, Okay, a polar protic solvent. What kinds of reactions can we expect to happen? Yeah, SN1, E1, and E2. On the other hand, if we have an aprotic solvent, we can expect SN2 and E2. All right, temperature-wise, if we have a cold reaction at 0 degrees Celsius, it is substitution. If we have a hot temperature, heat, or if you see this delta symbol, this triangle, that's elimination. Okay, so heat favors elimination. That's an important concept. Heat is going to favor elimination. This right here, by the way, this is something that can help us differentiate between SN1 and E1. Because you see right above it, we have such fierce competition, temperature can help us differentiate. All right, next up. If we have a mechanism where we're forming a stable carbocation, that is SN1 or E1. Right? If we have a reaction where we have a bulky base, E2. Now the classic example of this bulky base, tert butoxide. Okay, classic example is tert butoxide. Racemic mixture of products, that's an SN1 reaction. Okay, if we get a racemic mixture, that's an SN1 reaction. And lastly, if I have a methyl substrate, okay, like CH3 and then any sort of halide, the only reaction that is ever going to undergo is SN2. And that's precisely why it's not in this flowchart. Because no matter what kind of reagent I use, a methyl substrate will undergo SN2. All right, so keeping this flowchart and all this knowledge in mind, I have this example alkyl halide, secondary halide, and I want y'all to take a couple minutes, work through this, pause the video, and then we'll come back and analyze this. Time to work on this. The first thing I'm going to do is I'm going to analyze my conditions and my substrate. My substrate is actually the first thing I'm going to look at. So what kind of substrate am I working with? Secondary. This is a secondary substrate. So if I go back up to this flowchart, my secondary substrate, now I immediately have to think, all right, any one of these four could work here. Okay, so it's a secondary substrate, everything is on the table. So I'm going to start at the very top here. I'm going to label this reaction. Actually, I'm not going to do that. Okay, so secondary substrate, I'm reacting it with water at 0 degrees Celsius. Now, to me, the first thing that actually stands out here is that 0 degrees Celsius. So to me, this implies substitution. Right? This is substitution. So this is either SN1 or SN2. If it's SN1, I'm going to be using a weak nucleophile. If it's SN2, I'm going to have a strong nucleophile. So I look at my reagent here. My reagent is water. And we know that water is a weak nucleophile. So consensus here, this is an SN1 reaction at the top. These are SN1 conditions. So my product, we just said that my product is always going to be, or usually going to be, a racemic mixture. So it's going to be that alcohol and that alcohol. I'm going to get a racemic mixture of enantiomers here. These are my products. Moving along down here, I have sodium azide. Ooh, immediately, strong nucleophile. Sodium azide is a strong nucleophile, and I have a polar aprotic solvent. If I couldn't tell already, this is SN2. That sodium azide is a dead giveaway. Classic dead giveaway that this is an SN2 reaction, and the DMSO is just icing on the cake. So I have SN2 conditions with a strong nucleophile. Yes, it is a secondary alkyl halide, but it's a strong nucleophile in a polar aprotic solvent. That is, again, classic SN2 conditions. All right, Now at the bottom here, I have a very similar reaction actually to the top. I still have water as my reagent, but this time I have heat. So the heat, we said heat is indicative of elimination. Now the next thing is water a good base or a bad base? And water is a bad base, a weak base. So this is E1. And that right there is what I said the differentiating factor was. We said that SN1 and E1 were very fierce competitors, and we used temperature to differentiate between the two. So if I have E1 here, I'm going to go with just the most stable product, which is that most stable alkene. And then lastly, I have sodium ethoxide. Okay, so that is a strong nucleophile and a strong base. And then I have ethanol. Ooh, ethanol is a protic solvent. So even though I have ethoxide as a strong nucleophile, I'm in a protic solvent. And then I also have heat again. So again, the heat here, that's an elimination. And the polar protic solvent, well, it could be E1 or E2, but ethoxide is a strong base. So this is E2. So again, I'm going to end up with this. So just like that, we're able to use not only our substrate, but also our reagent and these additional considerations for the reaction conditions to really hone in on what reaction is happening. My recommendation on an exam is to just kind of use this flowchart as your framework. Look at your substrate, look at what kind of reagent you're working with. Is it a nucleophile, a base, or both? And then consider some of these. What does your solvent look like? What is your temperature? Is your base bulky, right? If you're given the products, is it a racemic mixture or just a mixture in general? And then is your substrate, is it a methyl substrate? Right? If it's a methyl substrate, that narrows down your answer extremely quickly. So I would use this framework as you're practicing to really try and hone in and kind of get used to what you can expect to see for each of these 4 reactions. And with a little bit of practice and some time, I think you'll be all set and ready for your OChem exam. So if you enjoyed this video and found it helpful, please do leave a like. I'd love to hear your feedback and suggestions in the comments below. And I will catch you guys in the next video. Take care.